In the walls of the Grand Canyon, there is a place where one layer of rock sits directly on top of another. Nothing unusual to look at, just a boundary, a thin line running through the stone. But that line marks the disappearance of 1,200,000,000 years of planetary history. Not missing data, not a gap in our knowledge. The physical absence of rock that should be there. Something erased this chapter of Earth's record so thoroughly that for 150 years, the best geologists on the planet could not agree on what had done it. Before we go any further, please subscribe to this channel. Your support genuinely helps us keep making films like this one. Thank you. Now, let's talk about what it means for time itself to go missing. Geology, at its foundation, rests on a principle so simple that children grasp it intuitively. Things that happened earlier are buried beneath things that happened later. Walk down into any canyon, any road cut, any exposed cliff face, and you are walking backward through time, layer by layer. Each stratum a page in a book, written by the planet itself, one grain of sediment at a time, over spans of time that make human history look like a rounding error. This principle, superposition geologists call it, is one of the oldest and most reliable tools in the entire discipline. Lower is older, higher is younger. The rule almost never breaks, except when it does. Except when you find a boundary where the book simply skips. Where the last page you were reading was written 500 million years after the first page of the next chapter should have appeared, and instead the two pages are pressed directly against each other, with nothing, no transition, no gradual change, no fossils marking the intervening eons in between. Before we go further into Powell's discovery itself, it is worth understanding exactly how geologists came to trust the layered rock record in the first place. Because the confidence with which scientists can later declare a piece of that record missing depends entirely on how solid the underlying method is. The principle of superposition was first formally articulated not by a geologist in the modern sense, but by a 17th century Danish scientist and Catholic bishop named Nicholas Steno, working in Italy in the 1660s. Steno was studying the layered rock formations of Tuscany, and he noticed something that seems obvious in hindsight, but had never been clearly stated before. That in any undisturbed sequence of sedimentary rock, each layer must have been deposited on the top of the layer beneath it, meaning the layers at the bottom are, by simple logical necessity, older than the layers above them. This sounds almost too simple to be called a scientific breakthrough, but it laid the conceptual foundation for everything that would follow in the science of stratigraphy, the study of rock layers and what they reveal about the passage of time. Over the following 2 centuries, geologists refined this basic insight into an extraordinarily powerful analytical tool. Each layer of sedimentary rock, geologists came to understand, is not merely a record of when it was deposited, but a record of the specific environmental conditions present at that moment. The type of sediment, the presence or absence of fossils, the chemical composition of the rock, even subtle features like ripple marks or mud cracks, all preserve information about ancient rivers, ancient seas, ancient deserts, ancient forests, layered one atop another in a sequence that, when read correctly, tells the story of an entire landscape's history across millions or even billions of years. By the time Powell set out down the Colorado River in 1869, this method had already produced remarkably detailed reconstructions of Earth's history in well-studied regions of Europe. Geologists had identified and named entire geological periods based on the characteristic rock layers and fossil assemblages found in specific locations. The Cambrian period itself takes its name from Cambria, the Latin name for Wales, where the rocks of that age were first systematically studied. The layered rock record, in short, was already trusted as one of the most reliable sources of deep historical information available to science, precisely because it followed such simple, verifiable physical rules. This is exactly why the Great Unconformity felt so disorienting when Powell first encountered it. It was not simply an absence of information. Geologists were used to gaps, used to incomplete records, used to rock formations that had been destroyed by erosion in one place while surviving intact somewhere else. What made Powell's discovery different was the sheer, undeniable scale of the boundary itself, and the way it seemed to violate the orderly, continuous storytelling that the rest of the rock record so reliably provided. Between the ancient schist and the much younger sandstone, there was no gradual transition, no thinning sequence of intermediate layers marking a slow withdrawal of the sea or a gradual uplift of the land. There was simply an edge, sharp, abrupt, and, once its true age difference was eventually calculated, using techniques not yet available in Powell's lifetime, almost impossible to believe. It would take several more decades and the development of radiometric dating in the early 20th century before geologists could actually quantify just how much time the Great Unconformity represented. Powell himself, working only with the relative dating tools available to 19th century science, could recognize that something extraordinary had happened at that boundary. But he had no way of knowing that the gap he was staring at, in the deepest recesses of a canyon he was risking his life to explore, represented more than 1 billion years, a number so large that it would remain almost inconceivable even to the scientists who eventually calculated it. This is the Great Unconformity. And to understand why it has haunted geology for 1.5 centuries, you first need to stand, at least in your imagination, at the bottom of the Grand Canyon, on the banks of the Colorado River, in the exact spot where an explorer named John Wesley Powell first noticed something was deeply, structurally wrong with the story the rocks were telling. Powell was not a geologist by training in the formal academic sense. He was a one-armed Civil War veteran, a professor of natural history, and above all, an explorer, driven by a restless curiosity that would eventually make him one of the most consequential scientific figures in the American West. In 1869, he led a small expedition of 10 men in 4 wooden boats down the uncharted length of the Colorado River, through canyons that no expedition of European descent had ever mapped, on a journey that nearly killed most of the men who attempted it. Somewhere along that journey, in the depths of what would later be named Grand Canyon, Powell noticed something in the canyon walls that struck him as geologically impossible. At the bottom of the canyon, near river level, sits a dark, twisted, crystalline rock called the Vishnu schist. Metamorphic rock, meaning rock that has been so thoroughly cooked and compressed by heat and pressure deep within the Earth's crust that its original mineral structure has been completely transformed. The Vishnu schist is old. Not old in the way a Roman ruin is old, or even in the way a dinosaur fossil is old. It is old in a way that strains ordinary human comprehension. Approximately 1,700,000,000 years old, formed when the supercontinent that existed at the time was still assembling itself from fragments of even older crust, in an era so distant that complex multicellular life would not evolve for another billion years. And directly on top of the Vishnu schist, not gradually, not with any transitional layer, but abruptly, as though someone had taken an eraser to the intervening history, sits the Tapeats sandstone. This is also ancient by any human standard, approximately 525 million years old, deposited during the Cambrian period, the geological age immediately following one of the most consequential events in the entire history of life on Earth. But compare the two numbers: 1,700,000,000 years, 525 million years. The difference between them is not a few million years of ordinary geological quiet. The difference is approximately 1,200,000,000 years, a span of time so vast that it exceeds, by a considerable margin, the entire history of complex multicellular animal life on this planet, an interval longer than the time separating us from the first vertebrates, longer than the time separating us from the first land plants, longer, in fact, than nearly every other span of time discussed on this channel, compressed into a single boundary you could cover with the palm of your hand. Powell recognized immediately that this was strange. He documented it in his expedition notes, and the formation would eventually come to be known, in the language of geology, as an unconformity, a general term for any place in the rock record where the orderly, continuous deposition of sediment has been interrupted. Unconformities themselves are not rare. They happen constantly, all over the world, wherever erosion strips away rock faster than new sediment can be laid down, or wherever tectonic uplift exposes older material to the elements before subsequent burial resumes. A typical unconformity might represent a gap of a few thousand years, or a few million. Geologists find them everywhere and rarely think twice about them. What Powell had found was different in both scale and character. This was not a modest pause in deposition. This was an erasure of geological time on a scale that, when its full implications were later understood, would come to be called simply the Great Unconformity, capitalized, singular, as though there were only one, because for the region Powell was exploring, functionally, there was. And here is where the story becomes genuinely unsettling, in the specific way that only deep-time geology can be unsettling. Because as researchers over the following decades began examining rock exposures in other parts of North America, and eventually other continents entirely, they kept finding the same pattern. Not an identical gap in every location. The exact ages and durations varied from place to place, but the same fundamental structure: ancient, deeply metamorphosed basement rock, sitting directly beneath much younger sedimentary layers, with an enormous, unexplained gap in between. And that gap consistently terminating at approximately the same point in geological time, right around the boundary of the Cambrian period, roughly 540 million years ago, give or take, in the Rocky Mountains of Colorado, in the ancient shield rocks of Scandinavia, in the vast sun-baked interior of Australia, in the North China Craton, one of the oldest and most geologically stable pieces of continental crust on the planet, a region that has remained largely undisturbed by the violent tectonic reshuffling that has repeatedly torn apart and reassembled most of the rest of Earth's surface. Wherever geologists looked, on continent after continent, in rock formations separated by thousands of kilometers, and in some cases by entire oceans, they found variations on the same unmistakable signature: a missing chapter, its edges strangely aligned across the entire planet, as though the whole surface of the Earth had, in some coordinated fashion, had a significant portion of its own history quietly removed. This is the detail that transforms the Great Unconformity from a regional curiosity into one of the most genuinely puzzling problems in the entire field of geology. A gap in one location, however large, could plausibly be explained by local circumstances. A particular river system that happened to erode unusually deeply, a particular tectonic event confined to one region. But a gap that appears, with remarkable consistency, on nearly every continent, terminating at approximately the same geological moment, demands a planetary explanation. Something happened to the entire Earth, or something close to it, that was capable of stripping away rock on a truly global scale, and doing so with enough uniformity that the scars left behind a billion years later still bear the same essential signature, no matter where on the planet you go looking for them. For most of the 20th century, geologists working on this problem converged on two broad candidate explanations, and the debate between them would eventually stretch across more than a century of research, careers, and increasingly sophisticated dating techniques. The first explanation reaches back to one of the most extreme and, for a long time, most controversial hypotheses in the entire history of Earth science. The idea that our planet, at various points deep in its past, became almost entirely encased in ice, a state that researchers have come to call Snowball Earth. The evidence for Snowball Earth events is genuinely extraordinary and worth pausing on, because it establishes just how physically plausible an ice-driven explanation for the Great Unconformity actually is. During the Cryogenian period, roughly 720 to 635 million years ago, multiple independent lines of geological evidence, glacial deposits found at what were, at the time, tropical latitudes, distinctive banded iron formations that only form when oxygen-starved deep ocean water is suddenly exposed to atmospheric oxygen, suggesting an ocean sealed beneath ice for an extended period. and the peculiar chemistry of certain carbonate rocks that appear to have formed in the immediate aftermath of a dramatic global thaw, all point toward a planet that, at least twice during this era, became so cold that ice sheets extended from the poles all the way to the equator, encasing the majority and possibly the entirety of Earth's oceans and land masses in ice that may have been more than a kilometer thick in places. Try, for a moment, to hold that image in your mind with the seriousness it deserves. Not a particularly severe ice age of the kind that has come and gone repeatedly throughout the more recent history of our planet, leaving glaciers across the higher latitudes while equatorial regions remained temperate. A Snowball Earth event, if it occurred as the most extreme models suggest, would have transformed this entire world, every ocean, every continent, equator included, into something closer to the surface of a moon orbiting one of the outer planets. A frozen, largely lifeless expanse, illuminated by a sun whose warmth could barely penetrate the ice, for a duration that current estimates place somewhere in the range of millions of years at a time. Glaciers of this scale, advancing and retreating repeatedly across the surface of continents over millions of years, are capable of extraordinarily destructive erosion. A glacier is not a passive sheet of frozen water sitting quietly atop the landscape. It is a slow-moving, immensely heavy mass of ice, embedded with rock fragments that act as an abrasive, grinding relentlessly against the bedrock beneath it, as it flows, however slowly, under the pressure of its own accumulated weight. Modern glaciers, operating on timescales of mere thousands of years, are known to carve out entire valleys, strip away meters of solid rock, and reshape landscapes in ways that remain visible for millions of years afterward. Scale that erosive power up to a planet-wide ice sheet, grinding continuously for millions of years rather than thousands. And the proposition that Snowball Earth glaciation could have stripped away kilometers of continental rock, precisely the kind of erosion needed to produce the Great Unconformity, becomes not just plausible, but, to many researchers working through the latter half of the 20th century, the single most compelling explanation available. The timing seemed to fit as well. The cryogenian glaciations occurred within striking distance of the upper boundary of the Great Unconformity Gap in many locations, close enough in geological terms that a causal relationship seemed not just possible, but almost elegant. Here, at last, was a mechanism capable of explaining a genuinely planetary phenomenon. A planetary catastrophe. Ice, not fire, had apparently rewritten the rules of what the rock record could preserve. But the Snowball Earth hypothesis, elegant as it was, always carried within it a set of problems that never quite resolved cleanly. For one, the Great Unconformity, in many of the locations where it has been most carefully studied, appears to have begun forming well before the cryogenian glaciations are believed to have started, sometimes by hundreds of millions of years. If Snowball Earth glaciation were the primary sculptor of this global gap, the erosion should track closely with the timing of the ice ages themselves. Instead, in location after location, researchers using increasingly sophisticated dating techniques found evidence that significant portions of the missing rock had already vanished long before the coldest chapters of the Cryogenian ever began. And this is where the second explanation enters the story, a hypothesis that had always existed alongside the Snowball Earth model, competing for the same explanatory territory, but that lacked, for a very long time, the kind of decisive physical evidence needed to settle the question. The second explanation points not to ice, but to the deep, restless machinery of plate tectonics, specifically to the assembly and eventual breakup of an ancient supercontinent called Rodinia. Rodinia is one of a handful of supercontinents that geologists believe have formed and broken apart repeatedly across Earth's 4.5 billion year history, part of a grand, recurring cycle in which the planet's land masses periodically collide into a single unified mass, only to fragment again millions of years later, driven apart by the same convective forces deep within the mantle that first pulled them together. Rodinia assembled roughly 1 billion to 1.3 billion years ago, and it began breaking apart somewhere around 750 million years ago. A timeline that places its formation and fragmentation directly across the same span of Earth history that the Great Unconformity appears to span. The tectonic hypothesis proposes something more geologically mundane than a frozen planet, but no less consequential in its ultimate effects. That the immense forces involved in assembling a supercontinent, continental plates colliding, crumpling, and thrusting upward against one another with the accumulated force of the entire planet's tectonic system, pushed vast stretches of ancient, deeply buried crust up to the surface, exposing rock that had previously sat kilometers underground, safely insulated from the erosive effects of wind, rain, and river. Once uplifted and exposed, this ancient rock would then have been subjected to hundreds of millions of years of ordinary weathering and erosion, slowly, patiently stripped away layer by layer, grain by grain, carried off by rivers and deposited elsewhere, until eventually, once the supercontinent broke apart and new seas advanced across the eroded, flattened landscape, fresh sediment, the sediment that would eventually become rock like the Tapete sandstone, began accumulating directly atop whatever ancient basement rock happened to remain. On this model, the Great Unconformity is not the signature of a single catastrophic ice age, but the accumulated residue of an entire supercontinent cycle. Uplift, followed by hundreds of millions of years of patient erosion, followed eventually by renewed burial. Slower than glaciation, less visually dramatic, but potentially just as capable of stripping away kilometers of rock, given enough time. Before moving to how the debate was eventually resolved, it is worth dwelling on just how strange the Snowball Earth hypothesis actually is, and why it took geologists so long to take it seriously in the first place, because the story of that hypothesis is itself one of the more remarkable episodes in the history of Earth science. The idea that the entire planet could freeze over, equator included, was first seriously proposed in the 1960s by a geologist named W. Brian Harland, who had noticed something puzzling while studying ancient glacial deposits in Svalbard, an Arctic archipelago north of Norway. The deposits he was examining showed unmistakable evidence of having been formed by glaciers, the characteristic scratches left by rocks embedded in moving ice, the jumbled, poorly sorted sediment typical of glacial debris. But when Harland and later researchers calculated where these particular rock formations would have been located on the globe at the time they formed, based on the paleomagnetic signatures locked within them, essentially a record of Earth's magnetic field frozen into the rock at the moment of its formation, which reveals the latitude at which that rock originally formed, the results were startling. These glacial deposits appeared to have formed not near the poles, where glacier exists today, but at or near the equator. For years, this finding was met with considerable skepticism. Glaciers at the equator seemed, on its face, almost absurd, proposing conditions so extreme that many researchers assumed there had to be some error in the paleomagnetic measurements, or some alternative explanation that did not require the entire planet to have been blanketed in ice from pole to pole. It was not until the 1990s when a geobiologist named Joseph Kirschvink formally coined the term Snowball Earth and began assembling a broader body of supporting evidence that the hypothesis gained serious traction within the scientific community. The physics of how such an event could occur, once researchers began modeling it seriously, turned out to be genuinely alarming in its own right. Ice reflects sunlight far more effectively than open ocean or bare rock, a property scientists call albedo. As ice sheets expand from the poles toward the equator, they reflect an increasing proportion of incoming solar energy back into space, which cools the planet further, which allows the ice to expand even more, which reflects even more sunlight. In a self-reinforcing feedback loop that once it passes a certain critical threshold, becomes essentially unstoppable, using any mechanism available on the planet's surface. Climate models suggest that once global ice coverage reaches somewhere around 30 to 40%, this runaway feedback loop can take hold entirely on its own, rapidly locking the entire planet into a fully frozen state within a geologically short period of time, potentially just a few thousand years. An eye blink compared to the millions of years the frozen state itself would then persist. Escaping from a Snowball Earth state turns out to be almost as extraordinary as falling into one. With the entire ocean sealed beneath ice, the normal processes that regulate atmospheric carbon dioxide, primarily the weathering of exposed silicate rock, which naturally draws carbon dioxide out of the atmosphere over time, would have essentially shut down completely, since there was no exposed, unfrozen rock left anywhere on the planet's surface for weathering to act upon. But volcanic activity deep within the Earth continues, regardless of surface conditions, continuously pumping carbon dioxide into the atmosphere from below. With the primary mechanism for removing that carbon dioxide disabled by the ice itself, atmospheric concentrations would have built up steadily for millions of years, until they eventually reached a level high enough to trigger an extreme greenhouse effect powerful enough to overcome the ice's reflective advantage and begin melting the planet from the poles inward. The resulting thaw, once it began, would likely have been catastrophically rapid by geological standards, transforming the planet from a frozen wasteland into an intensely hot, humid, hothouse world within a remarkably short span of time, accompanied by torrential global rainfall as the enormous reserves of atmospheric water vapor and carbon dioxide worked their way back into equilibrium. This is the mechanism that, for decades, made Snowball Earth glaciation such a compelling candidate for explaining the Great Unconformity, a planet-wide ice sheet, advancing and retreating not once, but potentially several times across tens of millions of years, grinding continuously against exposed continental rock, with the combined weight of the entire cryosphere, offered a mechanism of erosion almost unmatched in scale by anything else in the geological record. If any process was going to strip away kilometers of solid continental crust across the entire surface of the planet simultaneously, a global ice age of this magnitude seemed, for a long time, like the most obvious candidate available. For decades, these two hypotheses, Snowball Earth and supercontinent tectonics, existed in a kind of scientific standoff, each supported by real evidence, each explaining some aspects of the Great Unconformity better than the other, neither one fully accounting for the entire global pattern on its own. Some researchers suspected the truth might involve both mechanisms working in combination at different times and in different locations, compounding each other's effects. Others argued for one explanation over the other, with genuine scientific conviction, based on the specific evidence available from the specific rock formations each had spent their careers studying. What the field lacked for 150 years was a way to directly date the process of erosion itself, not merely the age of the rock layers above and below the gap, which tells you only the boundaries of the missing time, but the actual, continuous history of what was happening to the ancient basement rock during the vast stretch of time when it was exposed at the surface, slowly wearing away. This changed with the development and refinement of a technique called thermochronology, and its more specific and increasingly powerful application, hematite uranium-lead dating, which is precisely what began to break the case open in the research published over the past 2 years. Thermochronology works on a beautifully elegant physical principle. Certain minerals, as they cool from higher temperatures deep within the Earth's crust to the cooler temperatures found near the surface, begin retaining measurable traces of radioactive decay. Specifically, in this application, the extraordinarily slow, extraordinarily reliable decay of uranium into lead, occurring at a rate that has remained essentially constant since the formation of the solar system. Below a certain temperature threshold, different for different minerals, but generally corresponding to a specific depth within the crust, these radioactive decay products become locked in place within the mineral's crystal structure, effectively starting a clock. By measuring the accumulated ratio of uranium to lead within these minerals today, researchers can calculate, with remarkable precision, exactly when a given sample of rock cooled below its particular temperature threshold, which, because temperature within the Earth's crust increases predictably with depth, corresponds directly to when that rock reached a specific depth beneath the surface, as it was being uplifted and simultaneously eroded from above. In practice, this means that geologists can now reconstruct not just the beginning and end points of an erosional gap, like the Great Unconformity, but the actual pace and timing of the uplift and erosion process itself, tracked mineral by mineral, sample by sample, across millions of years of otherwise invisible geological history. It is worth pausing here to walk through exactly how thermochronology works at the level of individual atoms, because the elegance of the method is part of what makes the eventual resolution of this debate so satisfying, and because understanding the mechanism helps explain why researchers trust these results with such confidence. Deep within the Earth's crust, temperatures rise steadily and predictably with depth, a relationship geologists call the geothermal gradient, typically averaging somewhere around 25 to 30 degrees Celsius for every additional kilometer of depth, though the precise rate varies depending on local geology. A mineral sitting 10 kilometers below the surface might experience temperatures approaching 300 degrees Celsius, hot enough that any radiogenic lead produced by the slow radioactive decay of uranium within that mineral's crystal structure remains mobile, capable of migrating and escaping rather than staying locked in place. But as tectonic forces gradually push that same mineral closer to the surface, whether through the immense compressional forces of continental collision or through the slower process of overlying rock being eroded away from above, the temperature surrounding it steadily drops. At a certain specific temperature, different for different minerals and different radiometric systems, something called the closure temperature is reached, the point at which the crystal structure becomes cool and rigid enough that any newly produced lead atoms become permanently trapped within it, unable to escape, effectively starting an atomic clock that will run uninterrupted for as long as that mineral exists. For the hematite uranium-lead system specifically, hematite being a common iron oxide mineral found throughout many of the ancient basement rocks associated with the Great Unconformity. This closure temperature sits at a relatively low point compared to many other radiometric systems, which turns out to be scientifically fortunate, because it means hematite crystals record the final stages of a rock's journey toward the surface with unusual precision, capturing exactly the kind of shallow, near-surface uplift and erosion history that researchers needed to distinguish between the competing Snowball Earth and tectonic hypotheses. By collecting hematite samples from multiple depths and multiple locations across a single rock formation, and measuring the precise ratio of uranium to lead preserved within each sample, researchers can reconstruct not just a single moment in time, but an entire trajectory, a detailed record of exactly when different portions of a rock formation passed through their closure temperature as they were carried toward the surface, essentially reading off the pace of uplift and erosion, the way you might read the speed of a vehicle from a series of time-stamped location markers along its route. This is precisely the technique that allowed the 2024 Pikes Peak study and the more comprehensive 2026 North China Craton study that followed it, to move beyond simply bracketing the Great Unconformity's beginning and end points, and instead reconstruct the actual pace and character of the erosional process itself. Data detailed enough to distinguish between the relatively uniform, geographically indiscriminate erosion pattern that global glaciation should produce, and the geographically concentrated, margin-heavy erosion pattern that tectonic uplift driven by continental collision should produce instead. The Pikes Peak granite, sitting beneath a particularly well-exposed section of the Great Unconformity in central Colorado, had long been a site of interest for researchers precisely because its geological history was relatively well constrained by other means, making it an ideal test case for any new dating technique. When the 2024 hematite analysis was completed, the resulting data told a clear story. Significant uplift and erosion in this specific location had already been underway for a considerable period before the onset of the cryogenian glaciations. This did not, on its own, definitively rule out a contributing role for Snowball Earth ice in later stages of the erosional process. The study's authors were careful to frame their findings as evidence for what geologists call diachronous development, meaning the Great Unconformity likely did not form as a single synchronized planetary event, but rather developed at different times and paces in different locations, driven by a combination of factors that varied regionally. But the finding was nonetheless a significant crack in the foundation of the Snowball Earth hypothesis as the primary, dominant explanation. If ice were doing the majority of the erosional work, the timing at Pikes Peak should have tracked much more closely with the known chronology of the cryogenian glaciations. Instead, the rock itself was telling researchers that substantial erosion had already occurred well before the ice arrived, meaning something else, operating on an earlier and independent timeline, had already begun stripping away the ancient crust long before the planet's coldest chapters began. In November of 2024, a research team applying hematite uranium-lead dating to rock samples from the Pikes Peak region of Colorado, a granite formation that sits directly beneath a well-studied exposure of the Great Unconformity, produced results that struck directly at the heart of the century-and-a-half-old debate. Their dating indicated that significant uplift and erosion in this particular location had already occurred well before the onset of the cryogenian Snowball Earth glaciations. If ice sheets advancing across the equator had been the primary force stripping away rock at Pikes Peak, the erosional signature preserved in the hematite should track closely with the known timing of those glaciations. Instead, the data showed erosion already well underway before the ice arrived, a finding difficult to reconcile with a purely glacial explanation, and considerably easier to explain if tectonic uplift, driven by the assembly of rodinia, had already begun exposing this ancient rock to the elements long before the planet's coldest chapters began. This was a significant result on its own, but it was, in a sense, a preview of a much larger and more decisive study that would follow just over a year later. In February of 2026, a research team, including geologists from Columbia University's Lamont Doherty Earth Observatory, published findings in the Proceedings of the National Academy of Sciences that represent, by the assessment of many researchers in the field, the most direct and compelling test yet applied to the century-and-a-half-old question of what caused the Great Unconformity. Rather than examining a single location, the team focused their thermochronological analysis on the North China Craton, one of the oldest and most tectonically stable pieces of continental crust anywhere on the planet, and, crucially, a region where the local geological history provides an unusually clean natural experiment for distinguishing between the two competing hypotheses. Here is the key logical structure of their approach, and it is worth walking through carefully because it explains precisely why this particular study proved so decisive. If Snowball Earth glaciation were the dominant cause of the Great Unconformity, the erosional signature preserved in the basement rocks of the North China Craton should show a clear, sharp pulse of accelerated erosion coinciding specifically with the timing of the cryogenian ice ages. A signature that should look essentially identical whether you examined rock samples from the stable interior of the craton or from its more tectonically active margins, because a global ice sheet, by its very nature, does not discriminate between geologically quiet continental interiors and their more actively deforming edges. Ice grinds uniformly across whatever lies beneath it. If, on the other hand, tectonic forces associated with the assembly and breakup of rodinia were the dominant driver, the researchers predicted they should see a very different and much more specific pattern. Significantly more intense erosion concentrated along the actively deforming margins of the craton, where the mechanical stresses of continental collision and rifting would have been most severe, contrasted with comparatively modest, more gradual erosion in the tectonically quiet interior, where the crust was simply sitting exposed to ordinary weathering rather than being actively uplifted by colliding plates. The team collected and analyzed samples from 5 separate sites across the craton, spanning both its stable interior and its more tectonically active margins, and the pattern that emerged from the data was unambiguous. As one of the study's co-authors put it directly, if glaciation had been the dominant driver, researchers would expect to see a clear pulse of erosion at the time of the cryogenian ice ages uniformly across all sample sites. That uniform glacial signature simply was not present in the North China data. Instead, the most substantial episodes of exhumation and erosion consistently correlated with the timing and intensity of tectonic activity at each specific site, heaviest along the actively deforming margins, comparatively modest in the quiet interior, precisely the pattern predicted by the supercontinent tectonics hypothesis, and difficult to reconcile with a model in which a planet-encasing ice sheet was doing the majority of the erosional work. After 150 years, after generations of geologists building careers around one hypothesis or the other, after decades in which the two explanations seemed permanently locked in an unresolvable standoff, the evidence had, for the first time, tipped decisively toward an answer. Not the ice, primarily, but the restless, grinding machinery of continents colliding, rising, and slowly wearing away. The assembly of an ancient supercontinent, written not in the rocks that survived, but in the staggering volume of rock that did not. The debate is not entirely over. Other researchers have already begun challenging the details of exactly how the North China data should be read. But the balance of evidence has shifted, for the first time in a century and a half, decisively away from ice as the primary cause. This is, in itself, a genuinely satisfying resolution to one of the longest-running open questions in the history of Earth science. But it is not quite the end of the story, because resolving how the Great Unconformity formed only sharpens the far stranger and more consequential question of what it means that this gap ends precisely where it does. Because here is the detail that elevates the Great Unconformity from a fascinating geological puzzle into something that brushes directly against the deepest questions this channel exists to explore. Across nearly every location where the Great Unconformity has been carefully studied, the missing chapter of Earth's history does not end at some arbitrary, unremarkable point. It ends with striking consistency in the immediate run-up to one of the most consequential events in the entire 4.5 billion year history of this planet. The Cambrian explosion, the geologically sudden and almost bewilderingly rapid diversification of complex animal life that occurred beginning approximately 538 million years ago. An event so abrupt and so transformative that it effectively marks the boundary between a world of simple, largely soft-bodied organisms and the world of complex, hard-shelled, actively predatory animals, whose descendants populate every ocean, forest, and continent on Earth today, including, eventually, us. For well over 1 billion years before the Cambrian explosion, life on Earth existed almost entirely as single-celled organisms, and later, simple multicellular forms. Organisms without shells, without eyes, without the elaborate body plans that define nearly every animal phylum alive today. Then, within a geological eye blink, a span of perhaps 20 to 25 million years, astonishingly brief by the standards of evolutionary time, nearly every major body plan that exists in the animal kingdom today appears more or less simultaneously in the fossil record. Arthropods with jointed legs and compound eyes. The first true predators, equipped with hardened mouthparts capable of tearing through the bodies of other animals. Organisms with hard shells, hard exoskeletons, mineralized skeletons of a kind that had never existed on this planet before. The Cambrian explosion is, without exaggeration, the single most dramatic burst of evolutionary innovation in the entire history of complex life, and its causes remain, to this day, one of the most actively debated questions in paleontology. And it begins almost immediately after the Great Unconformity ends. Is this connection meaningful in a genuine causal sense? Or is it, as some researchers have cautioned, simply a striking coincidence of timing? Two remarkable events in Earth's deep history that happened to sit adjacent to one another on the geological timescale without any deeper mechanistic link connecting them. The honest scientific answer is that this question remains actively contested, and any documentary claiming certainty on this point would be overstating what the evidence currently supports. But the possibility that a genuine connection exists is taken seriously enough by researchers working across multiple disciplines that it deserves careful consideration rather than dismissal. Consider what the end of the Great Unconformity actually represents, physically, for the chemistry of Earth's oceans. As the supercontinent Rodinia broke apart and sea levels rose, flooding the eroded, weathered landscape that 1 billion years of uplift and erosion had left behind, enormous quantities of newly exposed mineral material, phosphorus, calcium and other elements that had been locked away in ancient continental basement rock, inaccessible to the biosphere for the entire duration of the unconformity, would have been rapidly liberated by weathering and washed into the expanding shallow seas. Phosphorus, in particular, is a critically important nutrient for biological growth, and several research groups studying the chemistry of Ediacaran and early Cambrian marine sediments have documented significant spikes in phosphorus concentration occurring in the geological window immediately preceding and overlapping with the early stages of the Cambrian explosion. Calcium, similarly essential, not merely as a nutrient, but as the fundamental raw material for building mineralized shells and skeletons, appears to have become increasingly available in ocean water across this same critical interval, precisely the window during which the first hard-shelled animals begin appearing in the fossil record in significant numbers. The hypothesis, stated carefully and without overstating its current level of proof, runs as follows. The same tectonic process now identified as the primary cause of the Great Unconformity, the assembly and subsequent breakup of rodinia, with its accompanying billion years of continental uplift and erosion, may have functioned as a kind of vast, slow-acting chemical reactor, patiently accumulating an enormous reservoir of weathered mineral material across the exposed continental surface, only to release that reservoir suddenly and dramatically into the world's oceans as sea levels rose during the supercontinent's breakup, providing exactly the nutrient influx and mineral availability that the earliest animals attempting to evolve hard skeletal structures would have required. If this connection holds up under continued research, and it remains, it must be emphasized, an active and unresolved area of scientific investigation rather than settled fact. It would mean that the same tectonic upheaval capable of erasing more than 1 billion years of Earth's geological record was also, indirectly, patiently building the chemical conditions necessary for one of the most consequential evolutionary events in the history of life on this planet. Not erasure and creation as separate, unrelated processes occurring to happen near each other in time, but erasure as an essential, necessary precondition for what followed. 1 billion years of geological silence in this reading would not represent an absence of consequence. It would represent exactly the opposite. 1 billion years of patient accumulation, invisible in the rock record precisely because the process was one of removal rather than deposition, setting the stage, slowly and without witnesses, for the most dramatic flourishing of animal life this planet has ever produced. There is one more piece of this story worth examining closely, because it connects the resolution of the Great Unconformity debate to a broader pattern that researchers are increasingly recognizing across the entire history of the supercontinent cycle. The recurring, rhythmic process by which Earth's landmasses have repeatedly assembled into single unified masses and then broken apart again, stretching back across nearly the entire span of the planet's geological history. Rodinia was not the first supercontinent, and it would not be the last. Geologists have identified evidence for at least several earlier supercontinents, including one called Columbia, or sometimes Nuna, which is believed to have assembled roughly 1.8 billion years ago. and an even earlier landmass called Kenorland, dating back perhaps 2.7 billion years. Following Rodinia's breakup, the continents would eventually reassemble once more into the supercontinent Pangaea, roughly 300 million years ago. The same Pangaea whose eventual breakup, beginning around 200 million years ago, produced the modern configuration of continents we recognize today, and whose earlier assembly and later fragmentation drove the plume generation processes discussed elsewhere on this channel in relation to the mantle superblobs beneath Africa and the Pacific. This recurring cycle, assembly, prolonged tectonic quiescence, gradual breakup, followed eventually by renewed assembly on a timescale of several 100 million years, appears to be a fundamental, recurring feature of how this particular planet manages the immense heat generated within its interior, redistributing that heat through the slow, grinding movement of continental plates across the surface. Each supercontinent cycle, current research increasingly suggests, likely produces its own version of a Great Unconformity style erosional signature, though the examples from earlier cycles are, unsurprisingly, far more difficult to study, having themselves been substantially eroded, buried, or tectonically destroyed by the subsequent cycles that followed them. The Rodinia-associated Great Unconformity happens to be unusually well preserved and well exposed in locations like the Grand Canyon, precisely because the tectonic activity of the more recent Pangaea cycle happened not to disturb these particular regions especially severely. An accident of geological positioning that has left North America with an unusually clear window into this particular billion-year gap, even as equivalent gaps associated with earlier and even more ancient supercontinent cycles remained far more fragmentary and difficult to reconstruct. This broader context matters because it reframes the Great Unconformity not as a singular, one-time anomaly in Earth's history, but as a particularly well-preserved example of a process that has likely repeated itself in some form every few 100 million years, for essentially the entire span of Earth's geological history since plate tectonics first began operating on this planet, sometime in the first 1 billion or 2 years after its formation. Each supercontinent cycle represents its own extended interval of continental uplift, erosion, and eventual renewed burial. Its own missing chapter, written not in the rocks that survived, but in the staggering volume of material that did not, ground away over hundreds of millions of years by the same restless tectonic engine that continues to operate beneath our feet today, reshaping the surface of this planet on a timescale so vast that an entire supercontinent can assemble, dominate the surface of the Earth, and then dissolve again before a single mountain range has time to fully erode away. The Himalayas, still actively rising today as the Indian subcontinent continues its slow-motion collision with Asia, will themselves eventually be worn down to nothing, their material carried by rivers to the sea, deposited as new sediment, buried, and perhaps hundreds of millions of years from now, uplifted once again by some future tectonic event, exposed once more to erosion, contributing to some future geologist's discovery of a gap in the rock record, whose true cause will not be understood for another century and a half. The Great Unconformity in this light is not an aberration in how this planet works. It is simply the clearest, most legible example we currently have of something this planet has been doing patiently and repeatedly for billions of years, and will very likely continue doing for billions more, long after every trace of human civilization has itself become nothing more than a thin, easily overlooked line in some future rock formation, waiting for whatever comes after us to wonder what happened during the interval it represents. We do not yet know, with full scientific confidence, whether this connection is real in the strong causal sense the hypothesis proposes, or whether it will eventually be understood as a more limited, partial contributing factor, alongside other forces entirely. Changes in atmospheric oxygen concentration, shifts in ocean chemistry, unrelated to continental weathering, genuinely biological innovations in genetic regulation that made complex body plans possible for entirely independent reasons. Science, done honestly, resists the temptation to tie every remarkable coincidence into a single tidy narrative. And the true picture may well involve several of these factors acting in combination, each contributing something the others could not achieve alone. But consider, for a moment, what we can say with confidence, because it requires no speculative leap at all. For more than 1 billion years, roughly a quarter of the entire age of this planet, vast stretches of Earth's continental surface were being slowly, patiently, invisibly worn away, ground down by the same restless tectonic forces that built and then dismantled an entire supercontinent. Forces so gradual, so imperceptible on any human timescale, that not a single moment of the process left behind the kind of continuous physical record that geologists rely on to reconstruct history. We know this 1 billion years happened, not because we can read it directly, the way we read the pages that survived on either side of it, but because we can measure its absence with exquisite precision, tracing the cooling of ancient minerals as they were dragged, kilometer by kilometer, up toward a surface that was simultaneously grinding them away. And then, at the end of that immense silent interval, as the fragments of a broken supercontinent drifted apart, and the oceans rose to reclaim the weathered, flattened landscape left behind, something happened that had never happened before in the 4 billion years since this planet first formed. Life, which had spent the overwhelming majority of its existence as simple, soft, largely formless organisms drifting through ancient seas, began, within the span of a few tens of millions of years, a geological instant, to build itself into shapes of extraordinary complexity and permanence. Eyes appeared, jaws appeared, shells, skeletons, the hard architecture of predation and defense that would define the animal kingdom for the next 500 million years and counting, appeared with a suddenness that still, honestly, unsettles the researchers who study it most closely. Whether or not the missing 1 billion years and the sudden explosion of complex life that followed it are causally bound together in the way the emerging evidence suggests they might be, there is something worth sitting with in the simple fact that they sit adjacent to one another at all. that the longest sustained silence in the readable geological history of this planet gives way almost immediately to the loudest, most consequential burst of biological innovation this world has ever produced. 1 billion years of erosion, uplift, and patient, undramatic grinding, followed by an explosion of eyes and jaws and shells that would eventually, across an almost incomprehensible chain of further evolutionary events, produce every animal that has ever lived, including, at the very end of that chain, the species now capable of standing in the bottom of a canyon in Arizona, looking up at a thin line in the rock and asking what, exactly, happened to all that missing time. There is a final layer to this story worth sitting with, because it concerns not the geology itself, but the peculiar psychological experience of standing at the edge of a gap this large, and what that experience has meant to the people who have spent their careers studying it. John Wesley Powell himself, in the years following his 1869 expedition, would go on to become one of the most influential scientific administrators in American history, eventually serving as the second director of the United States Geological Survey and helping to establish the institutional foundations of American earth science as a formal discipline. But by his own later accounts, nothing in his subsequent career quite matched the specific, disorienting sensation of standing at the bottom of the Grand Canyon for the first time, looking up at walls that seemed, in his own words, to represent a kind of leaf torn from the book of time. A phrase that captures something important about how deep time geology actually feels to the people who study it most directly, as opposed to how it appears in the tidy summary of a textbook. Modern geologists who work regularly with the Great Unconformity describe a similar sensation, one that repeats itself each time a new researcher encounters the boundary firsthand, rather than simply reading about it in a paper. Rebecca Flowers, a geologist at the University of Colorado, who has spent years applying thermochronological techniques to exactly this problem, has spoken about the particular vertigo of running her hand along a single thin boundary line in an exposed rock face, and understanding, with full scientific precision, that her fingertip is tracing across more than 1 billion years in the space of a few centimeters, a physical gesture that takes perhaps 2 seconds to complete, moving across a gap of time so vast that, if you attempted to walk it out at the rate of 1 year per step, you would need to circle the entire Earth roughly 25 times before you reached the other side. This sense of scale is, in some ways, the entire point of studying deep time geology at all. And it is worth being explicit about why it matters beyond the immediate technical question of what caused a particular gap in a particular rock formation. Human beings are, by the nature of our own biology and our own comparatively brief lifespans, deeply unsuited to intuitively grasping durations of time on the scale that geology routinely demands. We can comprehend a human lifetime. We can, with some effort, comprehend recorded history, stretching back perhaps 5,000 or 6,000 years to the earliest written records of ancient civilizations, reaching further back into the tens of thousands of years separating us from the first anatomically modern humans, already begins to strain ordinary intuition. requiring deliberate effort and repeated comparison to hold the scale in mind with any real meaning. 1 billion years exceeds even the most generous human intuitions for deep time by a factor so large that comparison becomes almost the only useful tool available. If the entire 4.5 billion year history of Earth were compressed into a single 24-hour day, the billion-plus years represented by the Great Unconformity alone would occupy more than 5 hours of that day. Nearly a quarter of the planet's entire existence condensed into a gap thin enough to cover with a single fingertip. In a canyon wall that tourists photograph by the millions each year, most of them entirely unaware of what they are actually looking at. This is, perhaps, the deepest and most quietly unsettling implication of the Great Unconformity. Once you set aside the specific mechanics of ice sheets and continental collision and simply sit with what the gap represents, it is a direct, physical demonstration that the vast majority of Earth's history is not, and perhaps never will be, fully recoverable. That for every chapter of the planet's story that survives in a form we can read, there are almost certainly other chapters elsewhere that have been erased just as thoroughly. Their evidence ground down into sediment and redeposited so completely that no trace of the original rock, and therefore no trace of the specific history it once recorded, remains anywhere to be found. The Great Unconformity is unusual not because gaps like it are rare, but because this particular gap happens to be unusually well preserved, unusually well exposed, and unusually amenable to the kind of precise dating techniques that allow modern researchers to actually characterize its edges and, increasingly, its interior structure with real scientific confidence. Most gaps of this kind, scattered throughout the deep history of this planet, are not so cooperative. They simply exist as silence, unmarked and largely unstudied, because the rock that would allow them to be identified and dated has itself been destroyed. There is a term geologists sometimes use, somewhat informally, for this broader phenomenon: the incompleteness of the rock record, sometimes referred to as the imperfection of the geological archive. Charles Darwin himself grappled directly with this problem in the 1850s and 60s, recognizing that the fossil record his theory of evolution depended upon was, by its very physical nature, radically incomplete, that only a vanishingly small fraction of organisms that have ever lived were preserved as fossils in the first place, that only a fraction of those fossils survived subsequent geological processes without being destroyed, and that only a fraction of the surviving fossils have ever actually been found and studied by paleontologists. Darwin used this argument specifically to explain why the fossil record of his era failed to show the smooth, gradual transitions his theory predicted should exist between species. Not because those transitions never occurred, he argued, but because the geological processes responsible for preserving any historical record at all are simply too imperfect, too selective, and too destructive to reliably capture every chapter of a story unfolding across hundreds of millions of years. The Great Unconformity, understood in this light, is perhaps the single largest, most dramatic, and most precisely documented example of exactly the phenomenon Darwin was describing in more general terms more than a century and a half ago. Direct, measurable, physical proof that entire chapters of Earth's history, encompassing not just individual species or individual events, but more than 1 billion years of continuous planetary activity, can be erased so completely that only the most sophisticated modern dating techniques, applied with tremendous patience and precision, are capable of detecting that anything is missing at all, let alone reconstructing what specifically happened during the interval that vanished. And yet, in a strange and quietly hopeful way, the eventual resolution of the Great Unconformity debate demonstrates something equally important about the resilience and ingenuity of the scientific process itself. For 150 years, the physical evidence needed to settle this question simply did not exist in a form anyone could access, not because the evidence was permanently and irretrievably lost, but because the specific analytical tools required to extract it, tools capable of reading the cooling history of individual mineral grains with atomic-level precision, had not yet been invented. Powell, standing at the bottom of the Grand Canyon in 1869, could see that something extraordinary had happened at that boundary, but he possessed no method whatsoever for actually quantifying it, let alone explaining it. The geologists of the mid-20th century, armed with early radiometric dating techniques and the first serious models of Snowball Earth glaciation, could finally begin to estimate the scale of the missing time and propose genuine mechanistic explanations for it. But they still lacked the resolution needed to distinguish reliably between competing hypotheses that made similar broad predictions about timing. It was only with the refinement of hematite uranium-lead thermochronology, a technique that did not exist in any usable form until relatively recently, and that has only been applied to the Great Unconformity specifically within the past few years, that researchers finally gained access to the kind of fine-grained, site-by-site erosional history needed to actually settle a debate that had outlived every single geologist who had originally proposed either side of it. This is worth pausing on, because it represents something genuinely important about how scientific knowledge actually accumulates over time. Not as a single continuous march toward truth, but as a series of plateaus, sometimes lasting decades or even centuries, during which the available evidence simply cannot decide between competing explanations, followed by sudden, dramatic leaps forward whenever some new technological or analytical capability finally becomes available, capable of extracting information from evidence that had been sitting in plain sight, physically accessible for the entire duration of the plateau that preceded it. The rock at Pikes Peak and the basement rock beneath the North China Craton had been sitting exactly where researchers eventually found it for the entire 150 years the debate raged. The information needed to resolve the question was never lost. It was simply encoded in a form that 19th and 20th century science lacked the tools to read, locked inside individual grains of hematite in ratios of uranium to lead so precise that measuring them accurately requires instruments capable of detecting quantities of material far too small to see, let alone weigh, using any method available before the past few decades. This, perhaps, is the quiet lesson embedded within the resolution of the Great Unconformity debate. Beyond even the specific finding about tectonics and rodinia and the eventual timing of the Cambrian explosion. The billion-year gap in the rock record is not, in the end, a symbol of permanent, irrecoverable loss. It is a symbol of exactly the opposite. Evidence that even the most thoroughly erased chapters of this planet's deep history can, given enough patience, enough ingenuity, and enough time for the right technology to finally arrive, eventually be coaxed back into legibility, one carefully measured mineral grain at a time. The canyon walls that Powell found so disorienting in 1869 did not, in the end, keep their secret forever. They simply waited, patiently, for science to catch up with the scale of the question they were quietly posing the entire time. The rocks do not answer easily. They rarely do. But for the first time in 150 years, thanks to a handful of minerals patient enough to record the temperature of their own burial across 1 billion years of continental history, we are finally beginning to hear something close to a real answer. Not a legend, not a guess, but a measured physical account of one of the most consequential and least visible chapters in the entire deep history of this planet. The gap is not empty. It never was. It simply took us 1.5 centuries to learn how to read it.